is another theme. So the title, as was announced, is Non-triviality of Heegner points. And this was after, I think it's also said after Cornut, and using work of Moonen, I announced, but but this actually, I will explain why I don't use that. I'll try to do something simpler, actually. So, so Heegner points are points that correspond to elliptic curves with complex multiplication. So I'll first spend some time to explain the facts that I need about these elliptic curves with complex multiplications. And then this hour, so let's say it was 1, actually I will not speak about non-triviality of Heegner points, but I'll explain a result that is needed for the second lecture this afternoon. And this is the so-called a special case of the André-Oort conjecture that I will prove. And then the second hour, it will become, well, we will use this result and prove the non-triviality of the Heegner points, that the result that Cornut, is he here? So in case there is a, yeah, there. So if somebody has questions, you can also ask him. So let's start with the elliptic curves. So let E over the complex numbers now be an elliptic curve. Then, well, actually there are two possibilities. Well, in fact, there are infinitely many, but the endomorphism ring can be Z, or it is an order in a quadratic imaginary field. And just to spend no time, I mean, to just do this only once, so we will label these orders by the field and the conductor. This OKC is just Z plus C times OK. So O of K is the maximal order in this quadratic, so K quadratic imaginary field. So every imaginary quadratic field is possible, but and C is just an integer, say, greater or equal than 1. So all the orders in quadratic imaginary number fields are of this, I mean, even without the imaginary, are of this kind. That's basically because they are of rank 2 as a Z module, so you can just figure that out. So so you have these two possibilities. In the first case, you say that this elliptic curve has no complex multiplications, and in the second case, you say that the elliptic curve has complex multiplications by the field and with this given order. Okay, so for example, to show you how many elliptic curves with complex multiplications there are, let us take a look at the upper half plane. For tau in the upper half plane, the elliptic curve C modulo Z tau plus Z has Cm, complex multiplications, if and only if the degree of the field extension generated by over Q by tau is just 2. So even if you fix the quadratic field, then there is a very dense set of taus where you have these complex multiplications. Of course, which element you take in such a field will then determine the conductor. And then there's something funny, because if you fix the conductor, then there's only finitely many, up to the action of SL2 of Z. So, okay. Okay, so one basic thing we will have to know about these elliptic curves is the arithmetic of over which number field they are defined. And so how the Galois group of Q bar over Q permutes them. So this is the just some prerequisites here. Galois action. So CM elliptic curves are defined over Q bar. This is very easy to convince you, because if it were not the case, then the J invariant would be transcendental. And because complex endomorphisms is just an algebraic notion, you could argue that every elliptic curve with a transcendental J invariant had CM, right? Which is not the case. So they're defined over Q bar. So we have an action of Galois Q bar over Q somehow on these curves. So now we're going to look a bit closer at this action. So for K inside a given algebraic closure of Q, quadratic imaginary, and a C greater or equal 1, we will look at the following set. Put SKC. So I'm sorry that this looks a bit more complicated than necessary, but it's the set of pairs E over Q bar and alpha, where E is an elliptic curve over Q bar and alpha is an isomorphism from this ring of integers to end of E, with a condition such that the action on the tangent space at the origin of this elliptic curve, say on Lie of E, gives the chosen embedding of K into Q bar, right? Because apparently there are these two ways to embed K into Q bar, and I just want to have the set of these, right? So if this were wrong, then I could change alpha by the involution on this ring and then have it right. And so this is just, it's what you call fixing the CM type. Now, so the Galois group of Q bar over K acts on this set, right? Because if I just think of this elliptic curve defined by equations, I just apply an element of this Galois group to the equations, and then I get another one. So that's how this one acts. Now we also have another action, and this is but also the Picard group of OK. So this group was defined in Oosterlee's lecture, right? Well, maybe you have to say spec of OKC. It's the group of line bundles on the spectrum of OKC, or if you want, invertible, well, so locally, how do you say this? Projective modules of rank 1 over this ring. And the operation is the tensor product. So how does this group act? So if you have an L and an E, so L is supposed here to be one of these projective modules of rank 1, you want to write down the following thing, L tensor OKCE, right, where you just have to view this E as a kind of module over this ring, right? It's not in the sense that we do schemes over this or so. It's just, you could say in the language of functors that this represents, so L tensor OKCE. If I want to define a new elliptic curve, it suffices to say what its points are. And I'm working here with elliptic curves over Q bar, so if I just take the points with value in any Q bar algebra R, I want this to be just the tensor product of what you would think E R. Now I put the parenthesis here, right? So this makes sense. And now you just verify that this functor on R algebras is representable, and you get your elliptic curve. And it's actually very easy because you can, let me just write that down completely. You can just, there is always a surjection from the free module of rank 2 to this rank. You can always generate them by 2 elements. And because this is projective, this splits. So you get a projector in the 2 by 2 matrices. And so this means that if you apply this projector to E times E, you will get your E, well, you will get the thing that you want, right? It's very easy. So we have an action by the Picard group on this set. And also by this Galois group. And what you can see is that these actions commute. Right? That is because one is just doing operations that are defined over any field, and the other one just acts on the field over which you do the operations. So maybe the 2 actions. Commute. So also, let's write it a bit how this works over C. Over C, you can give the following presentation. You can give the following description. If E is just C modulo a lattice, right, and with the same condition that I know that this E, its endomorphism ring is this OK of C. So then lambda is an invertible OKC module, actually. This is not really obvious, but it has to do with the fact that this ring is of the form, you can generate it by 1 element over Z, which means that it is Gorenstein, and you can deduce from that if the endomorphism, so of course if this ring acts on this elliptic curve, if this is a modulo over this ring, then this lambda also has to be a modulo over that ring. But the fact that the endomorphism ring is not bigger means actually that it is an invertible module. That's nice. And if you want to do this tensor business, then L tensor E is nothing else than L tensor, say OKC, OKC E, C here. So this modulo, this is just another vector space, right, of dimension 1 over the complex numbers. And it contains this lattice here. Right, so this is how you can think of it. Okay, and what is very important in all this is the following thing. It is that this action on this set SKC by the Picard group is transitive and free. So basically you see that here because the choices for lambda as a module are just the invertible modules. So the action, so SKC is a pic OKC torsor, which just means that the action is transitive and free. Right? Okay, so that is a good thing. So actually, I claim this, well, these are over Q bar or over C, but it doesn't matter where you look at this. And over C, it's pretty obvious with these lattices. So it is a torsor. But then, as an immediate consequence, you have that this Galois action has to be of a very special kind. Because if you think of it, it commutes with this action of this Picard group. So the only things that commute, of course, I can just choose 1 element here and say that I have a bijection between this set and the Picard group. And this Picard group acts on itself by translations. And the only things that commute with this are usually the right translations. But the group is commutative here, so it's the same thing. So because the Galois group, the Galois action commutes with this Picard action, it has to factor through that Picard action. So the thing is that the Galois group of Q bar over K acts via a map, a morphism of groups to this Picard group. Right, and this is just a formal consequence. Now you can try to see a bit more. So basically what you can also do is to think about a moduli space for these for this kind of set SKC. If you just replace the Q bar by any scheme, you can still formulate this. Well, actually, then we, instead of demanding an isomorphism, it would be better to ask for an injection. Because if you want to do this over finite fields, the endomorphism ring might be bigger. Right? It might be super singular, and then you have quaternion algebras. But you can do this, and then you can see that this this action actually, where it has to, you can see where it is unramified.
If you take this only injection in characteristic 0, you get something bigger, or don't you get?
Oh yeah, I wouldn't get the same thing. That's true. Yeah. So what should I say? Say that it is. So how would I say this? Somehow I want to say that. If you, so suppose I would just say it injects and the co-kernel is torsion free. That would be a good thing, I think. Well, let's not worry about that, but I think that is the right thing. Okay, so this action, this is unramified at all primes not dividing this conductor. So this is one thing that you know that this, well, people doing number theory know this extension, right? I don't know what name it has, but if you take the conductor equal to 1, you just get this Hilbert what's it called? Class extension, right? I mean, and that one is unramified everywhere. So this is completely logical. And when it is unramified, by this I mean at primes of K lying over primes that do not divide C, right? For M, so now I want to describe the Frobenius elements. So for M, a maximal ideal in OKC with C not in M. So this is a prime, a maximal ideal that does not, of this, where it is unramified. You can figure out that the Frobenius at M maps to the class of M in the Picard group, and then you take the inverse. So this is, well, I mean, it's either this or not the inverse, but it is the inverse. So this is very nice. Oh, yeah, this also means that the map is surjective. This GK then surjects to the Picard group, because you know that this Picard group anyway, it's generated by all the classes of the maximal ideals. So this means that you get a field extension. You have K, and then you have an extension K square bracket C, where the Galois group here is this Picard group. Okay, that's the. Okay.
M is a prime ideal?
Yeah, so I said M a maximal ideal. Yeah. Well, yeah, maximal ideal that does not contain this conductor. So that describes the Galois action. Yeah. So now this is the end of the intermezzo, and now I want to get back to these to this André-Oort conjecture, of which I need a special case. So we're going to look at products of modular curves and subvarieties, and what the notion of special subvarieties. So let S be a finite set. Yeah, okay. And for every S in S, I take gamma S inside SL2Z a congruent subgroup. Okay. XS will be, or how do you? No, let me just. I'm going to look at the product of S in S for the X gamma S, where this X gamma S is just the upper half plane modulo the discongruent subgroup, but I view it as an affine algebraic curve over the complex numbers. Okay, so I have this product here, and I want to consider some closed irreducible subvariety Z inside X, a closed irreducible subvariety. Okay, algebraic subvariety. Then Z is called special if there exists, well, this is a slightly long definition, so if there exists a partition S is S1 disjoint union S2 disjoint union SR, say, together with following data, such that Z is actually the product of subvarieties Zi, where Zi is a closed irreducible subvariety of the product, say, of Xi, and Xi is the product for the S in Si of the X mod gamma S. So I just take a subproduct. So the thing is, I say you have to decompose this Hill product into groups of factors. In each group you have to take a subvariety that is of the following form, of one of the forms. So the Zi has to be of one of the forms. So the first possible form of this thing is very simple, a point, a CM point. So a point on the modular curve now is called special, or CM, if the elliptic curve that corresponds to it has complex multiplications. So we can say, okay, if a Zi is just one CM point, we call it special. And the second type is the image of a map from the upper half plane to this Xi under the map that sends tau to, say, well, so the S coordinate should be of the form GS times tau, so the class of one element, of such a thing with the GS in GL2 of Q plus. So an element of GL2Q with positive determinant. Right, this is the, so what I say is that it can either be a point, or you have to choose for every factor in this, for every gamma S here, you have to choose an element in GL2Q plus, and you just map tau into there. So it's a kind of curve, it's a modular curve again, embedded into this product of modular curves by some modular map. That's what it is. So, and yeah, so this is the end of the definition, right? So point. So those are the special subvarieties, and this is just an explicit characterization of what you call in arbitrary Shimura varieties. You have the notion of subvarieties of Hodge type. Well, these are the subvarieties of Hodge type of products of modular curves. And this André-Oort conjecture says something about CM points and subvarieties of Hodge type. So, yeah, this is the same as Hodge type, yeah, but I don't want to give the definition of what Hodge type is. And anyway, I have to use this special, this explicit description. So, so you can maybe guess somehow or if you know it already, the conjecture that says that if you take any subvariety in which the special points, the CM points are dense, then this subvariety has to be special. So somehow you want to characterize the subvarieties of a product of modular curves on which the CM point. So a point on the product of curves is called CM if all the coordinates have CM. Right? That is one of the that's the logical definition. So the special subvarieties should be precisely the subvarieties that contain Zariski dense sets of special points, of CM points. Special points, it's the same thing. So here we have the following conjecture by André-Oort. So Yves André and Frans Oort. Let sigma be a set of CM points in X as above, right? So X is this product. Then all irreducible components of sigma zar. So sigma zar is the Zariski closure of this set sigma. It's the smallest closed subset in the Zariski topology that contains these points. All irreducible components are special. So that's let me see. So then there is a theorem that I proved in 1999, but it's still not published. But oops, not as bad as yesterday. But I should publish it soon. So this is true if one accepts. So if one believes in the generalized Riemann hypothesis for imaginary quadratic fields. And unconditionally, for if you say in the case of a product of two modular curves, say if S has two elements, and this is a theorem of Yves André. Right, and actually maybe it's just true that you could do that one can also do the general case without the Riemann hypothesis. If for the case of two curves you just use this, then maybe you don't have to do anything very complicated to extend the result. Okay. So now for today now, for the next talk, I want to give a slightly easier version of this one that is enough for the next lecture. And so with a proof that I can give reasonably fast. So here is a version that is less strong but sufficient. So let K be a quadratic imaginary. Let K be quadratic imaginary, okay. And we even fix, well, this is not what you, so I'm not going to fix the conductor, but I'm going to fix the primes that divide the conductor. So I just take a positive integer and let sigma in X be a subset of CM points such that for every X in sigma and for every coordinate S, say, well, actually, I don't know why I did this with the set S and not with just 1 up to n, right? I should maybe have done that. I want that the endomorphism ring of this elliptic curve that corresponds to the point XS, so right? So XS is a point on one modular curve. It is an elliptic curve with some level structure. I just forget this level structure. I just say, okay, there is this elliptic curve. I want this to be O K of some conductor C that depends on X and S with the property that the prime numbers that divide this conductor are contained in the prime numbers dividing C. And one way to write this is that CXS divides C to the infinity. Okay? Somehow. Right, so this is one way to write that every prime that occurs in here occurs in there. Right, so for example, in the next lecture, we will just use one prime. So this is certainly strong enough for that. Okay, so that is the let. Then the conclusion is, then all irreducible components of this Zariski closure are special. So that's okay. So now I should make a remark. This last theorem follows from one of Moonen, who has a general result about this André-Oort conjecture. So you should look up in Compositio Mathematica 114, and this was in 1998. But his proof, well, he proves a general case, and when I gave the title for these lectures and the abstract, I thought that I could just easily adapt his proof to the case that we need and give a simple proof that still would somehow explain what the ideas are in Moonen's proof. But this was too hard for me, so too complicated. So it's not that there is a problem with it, but it's just this special case doesn't make it much easier. So it's not. And if you read it, you will see that it is quite complicated how to prove it that way. So I want to give a proof that is simpler. So I have half an hour to do this proof. So we're going to prove this last theorem. So we pick Z be an irreducible component of this Zariski closure. Okay, so we take one irreducible component, and now we're going to look at the projections. So maybe I should draw a picture somehow. Just think of a lot of modular curves, and inside you have a variety, and you don't know so much what it is, but we're going to prove what it looks like. You can look at all the projections. Consider the projections PS from, say, projection in the S direction from this Z to the X gamma S, right? We can just look at those projections. Now, so these are curves, right? So either this is dominant or the image is a point. And so the image dominant or constant. And if it is constant, I know that, this Z contains points like this. So if it's constant, then constant. So in that case, this projection has as image is a CM point, right? That is quite clear. And if this happens, then I can just say, okay, I can do with one factor less, because I don't have to change my variety and just look in one. I just remove the factor at this S. Right, so we can assume all projections to be dominant. So that's one thing. So now we have to look a bit better. Now all the projections are dominant. Now we're going to look at the projections to pairs of coordinates. right? And then we look at projections to triples of coordinates and so on. So, and in the end, we will get where we want. So now consider projections to pairs. Now if, say, a P S S prime, projection SS prime from Z to X gamma S times X gamma S prime. So I can do the same story. Now I know that the image in each of the factors is dominant. So the question now is, this projection to this surface can be two things. The image can be a curve or it can be the whole surface. So if the projection to this thing of Z, well, is not dominant, then if we assume the theorem for the case of two factors, we know what the image is. So this is what I'm going to do. I'm going to assume it for the moment for two factors, and then first do the case of arbitrary dimension, and in the end I'll say something about the two factors. But anyway, for the case of the two factors is well documented. I'll give references for that. Is not dominant, then the image is a modular curve, or is say the graph of a Heegner correspondence in the product of these two modular curves in X gamma S times X gamma S prime. And I can just replace this surface by this curve in it and continue my whole proof, because it just means that the image in this product is a modular curve. So I'm in the same situation by saying that now I'll just not look at the image in the whole product, but somehow the image in the product with one factor less. Right? We can replace X gamma S times X gamma S prime by this graph, right? By this new modular, this modular curve, right? Because the graph of a Heegner correspondence is just also a modular curve, so I can do that too. So now we are in the situation. So now we have that all these projections to pairs of factors are dominant. So that is nice. And once you know, well, now let us look again at the definition of special subvariety, right? It's there. Basically, this definition says that the only equations you want to have for, well, it says that the relations come from isogenies between pairs of coordinates. Right? That is what it says. It says that well, somehow you have to group the set of indices, and then for each subset in which you partition, you have points x1, x2, x3, and so on, and all these coordinates correspond to elliptic curves that are isogenous with isogenies of a given degree. So now I know that there are no such things anymore, because generically, I mean, this is a dominant map. So the only thing we have to prove now, so if we want to prove the theorem, we have to prove that our subvariety is the whole thing. That Z is X. Right? That is what we have to do. So now there will be some geometry, and well, a few things. And so actually if you want to just have one example in mind, then you should think of a product of 3 curves with a hypersurface in it that projects surjectively to the 3 coordinate hyperplanes. Right? So that is the situation that we are in, except that it can also be of higher dimension. So we can do a next reduction step now, because we have to prove that our subvariety Z is the whole product of these modular curves. We can now replace these congruent subgroups by SL2Z, actually. So replace the gamma S by SL2Z, which means just that we have this map X. X, say, was, so now suppose that S is just a set 1 to up to N. X maps to C to the N by doing the J invariant on every coordinate. This is a finite map. It's the well, it's not really a quotient because these subgroups are not normal, but this is just a finite map. On each coordinate, it has degree the index of this subgroup, say. And if I have a subvariety here, and I want to show that it is X, then I just have to show that the image here is C to the N. Right? That's the same thing. So, so we replace. So we replace X by C to the N and Z by its image. Its image in C to the N. Right? So now we are in the variety is easier now. So now we do induction on N. So what does that mean? That means that we assume the result for all lower values of N. So that is, of course, always allowed. We should still keep in mind that we have to prove the case for N equals 2, right? We shouldn't forget that. But so we may suppose that all pi from Z to C to the N minus 1. So here I just look at projections on coordinate hyperplanes, and that all these are dominant because of the same type of reduction as I did before. If one of the projections, suppose we do this induction, if one of the projections is not dominant, then I get a real subvariety there, and I can just say, okay, then I apply the result there, and I get a relation between 2 coordinates, and this was not the case. So now we have that the projections to the coordinate hyperplanes are dominant. So now we can start to do the arithmetic. So Z contains always this dense set of CM points. And these CM points are points that are defined over Q bar. So that means that this Z is also defined over Q bar. And if it's defined over Q bar, it's defined over a finite extension of Q. So that is a nice thing. So Z is defined over a number field F. So good. Now we take a prime number. So this is where we have to use some number theory. Take L prime such that, so what are the conditions? We want it to be at least 13. So that is we want L to be greater or equal than the degrees of all these PIs, these projections, 2 coordinate hyperplanes. And for every I, say. And we want L split in this ring here. So this means that L is split in K and prime to C and in F. Right, this last is maybe the toughest condition because we don't know how big this field is, but there exist primes that split, so we can always do this. So then we have, I think this fits here now. Let me make the following claim. I claim that yeah, okay, I have to explain a little bit what I'm doing, but I claim that Z is contained in the image of itself under some Hecke operator, namely with this TL. And what am I doing with this TL? So TL of, say, x1, xn is the set, is as a formal sum. I mean, I'm treating it as a subset, but usually when you do a correspondence, you count with multiplicities, but of x1 prime up to xn prime, where xi prime is, say, there exist isogenies from the curve that corresponds to xi to the curve that corresponds to xi prime of degree L. So basically what I'm doing is I'm taking a point in my C to the n. This point corresponds to an n-tuple of elliptic curves. In each of these elliptic curves, I'm going to make the list of all subgroups of order L. So this makes me L plus 1 to the power n subgroups. Then I look at all the quotients, and this is the thing here. Right? And now I claim that we have this inclusion. Good. So why is that? Proof. So here we use the Galois action, because now this variety is defined over the field F. So the Galois group of Q bar over F permutes the points of the Q bar points of this Z. So you cannot, and we can still use this to do something non-trivial. So for every sigma in the Galois group of Q bar over K, over F, sorry, and for every X in sigma, we can say the following thing. Sigma of X is in F, in Z, right? So that's because these points, because this doesn't move points out of my Z. The Z is defined over F. So now we take sigma is the Frobenius at M a maximal ideal over L, right? L is split in F, so I can take a maximal ideal there with, okay, so, and now, because of the way the Galois group acts on the special points, on these CM points, we can say the following, then sigma of X is in TL of X. This is simply because if you look at it's gone now, no doubt. But the Picard group of OKF was acting on the set of the set of these CM points, and the maximal ideal at each maximal ideal was just doing this tensor product. So this is very easy to verify. So in particular, this is in TL of Z. So, but this, this is also defined over F. So if I apply sigma inverse now, I see that X is in TL of Z, right? And this happens for every X in sigma. I should say that I have replaced sigma by its intersection with Z, of course. I mean, in the beginning of the proof, I said let Z be just one irreducible component, so I should restrict my sigma to the points in Z then. And then I can say this. So this happens for a dense set of points in Z, so Z has to be in TL of Z. So that's nice. Then comes the next claim. And this is where actually it helps that the dimension is big enough. TL of Z is irreducible. So this is nice because it will tell you that here we have equality. And so how do you prove that this is irreducible? And this here, I mean, over C or over F, that's the same thing. But the proof will show that it's irreducible over C, so that is even better. And the proof is group theory. If you, well, you make it into group theory. Wait. Okay, yeah, let me see. So, yeah, so to show this, I want to introduce some notation. So, so X will be this upper half plane. It will be the modular curve corresponding to the full level L congruent subgroup. So this is a cover of my C of my moduli space of elliptic curves, where here I have an action by the group SL2 of FL. Oh, this is not, oh, yeah, it's the same L as there. Modulo 1 and minus 1, right? So this group will be called G, and this is a finite simple non-commutative group. We will use that. So we have this thing, and if you think about how the Hecker correspondence is defined, we have this x to the n maps to c to the n. In here, so let's call this pi n, this projection. In here, I have my subvariety z, and I can look at this pi n inverse z here as a thing there. And TL of z, this maps surjectively to what you call this TL of z. Even to do this Hecker correspondence, you don't need to go all the way up with this group. You can use the Borel subgroup in there, but for other purposes, I want to use the group structure. I say, okay, if we want to prove that this is irreducible, it is enough to show that this is irreducible. So we are going to show that this is irreducible. So, and then it will follow that this is also irreducible. Actually, maybe, okay. So how do we do that? So let V be an irreducible component of this pi n inverse of z, right? So we would like to prove that it's all of it, and let H its stabilizer in G to the n, right? So this map from x to the n to Cn is the quotient for G to the n acting on x to the n. So, right, so G to the n acts on x to the n, and the quotient is this C to the n. So that's why the pi n inverse of z is stable under the action of G to the n, but inside, I mean, there is a stabilizer of this irreducible component. That's a subgroup. And if I can show that this H is all of G to the n, then I have proved that this V is everything. So to prove, H is G to the n. Right? If I do that, then we are fine. So that's good. So now we consider the following things. So yeah, let me start here. So I have V sits in pi n inverse of z. And this sits in x to the n. And this, and now I project to some coordinates, to some x to the n minus 1. So I just select n minus 1 factors, and I can project. And then I get something that is of the same dimension. This is why I do this, right? This C has dimension n minus 1. So this V also, and now this will be dominant here. And at the same time, I can look at the quotient. So here we have Z. This sits in C to the n, like here. And here we have my pi I, and we are in c to the n minus 1. All right, it's the same thing. Now let's just look at this part, these 4 things here. Well, no. Let's look at this mapping to c to the n minus 1 and x to the n. So I'm extracting this part. And here I have my z. So now I have a diagram where I just have, if up to birational things, just field extensions, right? And that's nice because this was my pi. And here I have my group g to the n minus 1 acting. And here I had my group h. And if I look at what happens here we have g to the n minus 1. Just here, the image, I'll have to deal with the image on g to the n minus 1 of my group h. So I just want to look at this fiber product here, say this is p index I. And now I claim that because of the way I chose L, this pi is irreducible. So why is that? So here I have a group, I have a Galois extension with group g to the n minus 1. And here I have my map p index I. Now the L I took was bigger than at least the degree of this map. But this G is SL2 of FL modulo plus or minus 1. So if this, and this is a Galois extension, say, right? So if this would not be irreducible, it would mean that there is a common, that these field extensions are not disjoint. It would mean that there is a sub-extension of this here contained in that. But it's an easy property to show that this group G to the n minus 1 has no non-trivial subgroup of index less than or equal than L, right? The biggest subgroups you can find are just take everything on all factors but 1 and a Borel subgroup on one other. So they have index L plus 1. Yes, so I should say that I should thank Serre for pointing out that in the previous version of what I said I had used 5 and there was a problem with 11. So, so the 13 is meant to make this work. Right? So if this property is true, if L is at least 13. So that means that this is irreducible, but this V has to go to it, right? So it cannot do anything. So V surjects to this pi. But then what you get is that H surjects to G to the n minus 1. So that is a great thing, because now you can just do an algebra exercise. I'll formulate this as a lemma. It says that if you have a finite, no, finite is not necessary. If you have a simple non-commutative group G, then the normal, how do you say? And if you have a subgroup that surjects to every, so that is in G to the n and it surjects to every G2, then it is actually everything. So lemma. G, a simple non-commutative group, n at least 2, H in G to the n, a subgroup, such that pi of H is G squared for every I subset of order 2, then this H cannot be anything else than G to the n. And then this I leave it to you as an exercise. You have to, I think this is called Coltschien's lemma. I don't know. Maybe this is, it looks like something that you would. I think Daniel Bertrand once told me that, but is he here? No? Okay, we can't ask him. Good. So, well, now, so what do we have? We have Z equals TLZ, right, in this case. And so there's one last thing. So all TL orbits So if I iterate this correspondence in C to the n are dense for the Archimedean topology. So this is not so hard to see if you just think about what happens if you take one tau and you take all these things that are isogenous. When the next step you have L plus one of them, then you have, I don't know how many. So, well, one way to think about this, to say this is the following. If you want to really make group theory, so you can look at SL2Z union the element L001. This you can look at the group that is generated by this. This is somehow taking into account your Hecke operator. This is just this group by which you divide. This group is contained, of course, in GL2 of Z1 over L, because the generators are in there, but you can easily verify that this contains SL2 of Z1 over L. And this, if you map it into SL2 of R, this is dense. Basically, you would like to see Z with 1 over L adjoint is dense in R, right? And this group is generated by additive subgroups, so there you are, right? So this we have seen this now. So now we have a control. Well, we have proved that Z has to be everything because it is equal to this, equal to TL times this, and so on. So Z is dense. So Z is X, right? That proves the result. Up that to the fact that I have not proved it for n equals 2. But anyway, it's time now. So for n equals 2, see Yves André's article. André, this is in Krelle. I think of, well, I don't know the year. Or see my article in Compositio Mathematica. It's the same one as Moonen, 114. Right, so the case with n equals 2 is a bit harder because you don't have this irreducibility result so easily. So that's why you have to work a bit harder. But anyway, it's in a smaller situation and this is well explained. Okay, so thanks.